All right. Yeah. Thanks for the introduction, and yeah, thanks for the invitation. Happy to be here, and let's get started. So I'm going to talk about democratizing autonomous driving with open science. So we just I co-founded this nonprofit. It's called Keshyap, based in Tübingen in Paris, and our mission is to advance the efficiency frontier of physical AI. So we start with autonomous driving. That's kind of been my specialty in my PhD and after as well. So this is where our focus is first. And we do it through fully and open and reproducible research. So there's two kind of paths of this. There's like the research that pushes the efficiency frontier. I'm going to talk a bit about that in another talk on Friday. So come watch that if you're interested. But today I'm going to focus more on the open science aspect and how the tools, simulators, data sets, things that we put out in open source can really push the paradigm and speed up progress in physical AI and autonomous driving in particular. All right, so I start with a very, very brief overview of the current frontier of AV research and also deployments. Marco, who will talk next, I think, leads a team at NVIDIA, which builds vision language action models for driving. I was also part of this team until recently, and this has really accelerated progress in AV deployments for NVIDIA and also for many other companies in recent 2024 to 2025. These models, to put it simply, they predict expert actions. So they're mostly trained by imitation learning from large human data sets, conditioned on visual world states. And the key difference between a VLA and the typical end-to-end models of let's say 2020, 2021, 2022 till last year is that these models have these reasoning traces in natural language. So here you can kind of see the vehicle that's deployed. It kind of says that it's waiting until the traffic light turns green and then it takes the action. So it's a typical VLA like you will see in many other sessions of robot learning workshops in this conference. Nice thing about these models is that because of the language component, they can do some kind of reasoning, which is difficult for vision only or models trained purely on driving data. So they have this sort of reasoning core that comes from sort of memorizing all of GitHub and doing a bunch of math equations in their training, which is also helpful in driving in kind of identifying things like causality, structure, deduction, which you need for the process of driving in rare cases. The other thing is the rare case handling. Specifically, this is still trained on a lot of human collected data, but if you have a few examples of a rare event, and every time you see this rare event, you also have a language chain of thought that comes along with it, saying something like, slow down for this animal on the road. Even if you've only seen an animal on the road 10 times or 100 times in your data set of thousands of hours, the fact that every time it comes along with this little chain of text, which always says there's an animal on a road, helps the model kind of use this very rare data in the most effective way. It can kind of associate all of these cases and handle these rare cases better. We also see that language is like a nice modality to help arbitration. So these VLA models are deployed and they really push the performance and comfort, but they're often in parallel with a classical stack, which has many other sensors and modular functionality. And having access to this reasoning trace makes it easier to decide when to hand control over to the backup stack compared to prior end-to-end systems. The other very nice thing is that these models can be trained on lots of data where all of the data is labeled almost automatically because you have the GPT 5.5s and Claude 4.8s of the world now, and these keep getting better. You can generate these sort of reasoning traces offline with really strong, powerful foundation models, which keep getting better. and then distill them onto distill this ability to predict the reasoning trace before the actions onto the policy in the car. But at the same time, these models have a lot of disadvantages. This text and action are not in any way enforced to be aligned. The model can say something in the text and do a completely unrelated action because there's nothing in the training objective that actually enforces this alignment. It's very hard to incorporate the full sensor suite that you have in driving systems in VLA models just because they are trained on so much internet data. They end up really looking only at vision and language and ignoring these newer LiDAR, radar modalities if you try to put them in. And at a fundamental level, there's 2 to 10 to 30 billion parameters in these VLAs, and most of them are kind of dedicated to memorizing facts, and most of these are not relevant. The driving policy doesn't need to know who the president of a country is or what the capital of a country is. Maybe there are some facts that are helpful, but these are not the most important ones. And there's lots of other things to say about this, but I guess one point I want to make here is that already this paradigm is depending a lot on open source. These VLA models, they are starting from pre-trained QN something like a open source model built by an LLM company, and that's the only reason we got this huge progress. The fact that we had really strong open models for reasoning. But in spite of these advantages, I'm going to claim that these models are quite inefficient. If you look at this particular one called AlphaMayo, which there's a paper out from last year, it's trained on 80,000 hours of curated expert data. We had some sessions about data, and data is important, but also the quality, the distribution, and so on. And given that you needed 80,000 in the end, it's safe to assume that you probably need 1 million hours of data collection at minimum to reach the data set scale for doing this. And 1 million hours is not a lot if you're well researched. It's 1,000 hours from 1,000 cars in a fleet. So yeah, and 1,000 hours is 40 days of driving. So if you do the math, this is not out of reach of a very well resourced billion-dollar company, which is why you see so many self-driving startups in the last couple of years. This is much more achievable than it was 5 years ago to get to the amount of data you need to train a strong policy. Also on the compute side, I say 60,000 GPU hours is a lot, but this is something like 500 GPUs for a week. And there are companies that are able to raise the resources to train on this amount of GPUs. And I think also as academics, you can apply for a compute grant at one of the big supercomputers, and maybe you have a shot of having this compute. But I think we can't be satisfied with this level of efficiency. I still think this is extremely inefficient. 1 million hours of data and 10,000s of GPU hours, I think is too expensive for this technology to really be democratized. The fact that so much cost goes into building these systems makes it very unlikely that any of the players that are able to put in these costs actually open sources it and makes it diffuse sort of to all the most vulnerable users, the people who need it the most. So currently you see that there's a few big cities where the business may make sense at some point that have access to the self-driving technology. So I think we really need to push the efficiency frontier. That's also what I mentioned, I talk about in terms of the research in the other talk, but I think independent of current research, we always want the whole community to contribute to pushing this research frontier, because there's always going to be new ideas. 5 years from now, maybe we're not talking about LLMs. There's a different paradigm of things, and this needs to be applied to pushing the best autonomous vehicles we have then. So towards this, I'm going to talk about a bunch of things that we are doing at this new nonprofit that simplifies and accelerates autonomous vehicle development for the open source community and tries to bring it to a state where we can have a strong frontier, frontier level open source self-driving stack. So the first thing is data sets. And we have seen this in language. We've seen this in generalist robots. Once you have a heterogeneous and diverse data set of enough scale, So in language, it was like Common Crawl, the internet. For robotics, we had OpenX embodiment, which was 10,000 hours of data collected from like 20 different robots. These kind of kickstarted the flywheel of people becoming serious about creating a strong pool of open data for research to build on. So after OpenX embodiment, we had a bunch of the PI papers, and like this kind of kickstarted a whole subfield in like robotics. I think um, in driving, we have lacked a bit like coordination and scale in these open source efforts. So one release which like I worked on last year, and like I'm quite happy that we managed to push this through, is at NVIDIA. We released the physical AI AV dataset. There's 2,000 hours of driving data from 25 countries, many of them in the EU. Like it's the largest data set of the scale that has multi-view camera data, LiDAR, it has annotations. It's like basically a very huge and like fairly uncurated driving data set to get you started. Also, a year earlier, we released this thing called OpenDV. This is 2,000 hours of dashcam data, which we got from YouTube. There's many, many more thousand hours of this, and there's research into how to convert this into multi-sensor rig data. Like there's a paper from Waymo at CVPR. But that aside, we have now these isolated large chunks of driving data, which are split into multiple driving data sets. Yet, I think there is very limited research that tries to use this full potential of the open data we have. Like most research focuses on one established data set and pushing performance on one benchmark, which we're also happy about. Like I think there's a lot of people contributing to the open benchmarks, and I think this is great, but we maybe want to aggregate this a bit more and diversify. So the reason I think it's really hard for people to work on multiple data sets together is it takes so much work actually to get all these data sets in a usable state. So if I need to like have my hands on all of the public driving data that's out there, first I need to download all of these data sets, which can be terabytes to hundreds of terabytes. I need to set up all of these, add environment variables. They're all in different formats. All of them have a different sensor rig, different cameras, even like some have fisheye cameras, some have pinhole cameras. Then you kind of realize like all of them have bounding boxes, but the labels are completely different. Some of them like call the person on a scooter a person. In some cases, it's a rider. It's like everything is ambiguous. And if you keep going, you kind of at some point realize that there are 24 different conventions for Euler angle rotations, and now you're lost, and like everything you implement has a bug. And yeah, once you're past all this, then you realize that none of the sensors in driving data are even synchronized. All of them come in at different millisecond timestamps with an offset. And this is even by design. And like, this really matters then for some applications. And once you have gone through all this, it is like really going to bring you back to the default of like, let me just work on one data set where I have the like tool set up already by someone else who put in this effort. But so this is one thing which we have like kind of taken on us to implement and like speed up for the rest of the community. We released this library now called 123D, which unifies basically all the most used public autonomous driving data sets into a common format, and like makes it super easy to use for typical machine learning workloads and many others. So for example, we have new scenes. I show like from our visualizer, like what you get out of the data format. This is like one of the early high quality data sets probably many people in this room have worked with. Waymo open data set, also like very nice data set from Waymo, very like nicely calibrated cameras. We have Argoverse, we have Kitty 360, this is from my former advisor. We also have these much larger, so this is like 1200 hours, but slightly noisier data sets like NuPlan. This is currently very popular, and like this is also in the framework, and the data set I just showed you, the 1700 hours from NVIDIA. And all of it you can just use with a pip install, basically. There's also the ability in this library to directly collect simulated data in the format. I'll talk about this in a second, but this lets you collect data in multiple sensor rigs and train policies that potentially can adapt to different sensor rigs at test time and do all sorts of interesting new directions based on this. And together we have already 3,300 hours of data supported, and we are quickly adding many other data sets and working with many partners to potentially have them open source some of their data that can be in this common pool. So Right. Let me go over a bit the pipeline of how you would work with a new data set. Maybe one more thing to mention is that since we have already implemented, like we've taken the painful work of implementing all of these coordinate conventions and stuff, right, for these data sets, it became really easy to add new data sets. Now you can just ask Cloud Code to refer to all of the other implementations that are in there, and given the documentation of your new data set, just add it. So the incremental effort of adding new data sets exponentially goes down once you have this sort of framework set up. So yes, like if you want to use this, we start with a data parser for an existing data set or collector. This is a very simple script. You can actually even load directly from, like, some of these require authorization tokens, but some tokens you can just grab them from AWS or Google Cloud or Hugging Face or wherever with a single command. This is the key to our format. We use this Apache Arrow thing. It's very cool. It can do this memory map stuff, which lets you load like very large data sets without having them actually on RAM, but only access the parts that you call for. And you can do this like synchronization problem, which I mentioned earlier. You can deal with this by sort of pre-computing a synchronization table. So this lets you load a bunch of data sets, define a certain frequency you want the data at, or certain like intervals you want the data at, pre-compute that and just load it as if you had created this customized data set. And it supports camera, LiDAR, ego state, the typical driving data set things, and can be extended to more. There is also like, yeah, we give it a Python API, but it is language agnostic. You can have other APIs to access this data format. And we have a nice visualizer, which I showed you all the results from before on. So we have all this data, great. Now what can we do with it? I said we want to like really accelerate self-driving policy development. One very exciting area is reinforcement learning, and simulators are kind of critical for that. And so we want to build together with the community sort of the tooling and also the simulation that lets you use this tooling to the maximum to build these efficient policies. So Buffer Drive, this is a very nice tool from some folks at NYU and also many other collaborators that lets you do very fast, very high throughput traffic simulation. So this is not sensors, this is just like something like this. And you can do reinforcement learning this. There was like a very nice paper that came out last year called GigaFlow, which showed that you can get very strong planners when you train in this sort of simulation. And what we did now is we just wrote a wrapper to 123D on Buffer Drive, which means like not only like you have access to like Waymo, which Buffer Drive was originally built for, but you can take any of the data sets in 123D and load them up in Buffer Drive. So we did this experiment where we had 3 different training data sets, Waymo, Argoverse, and Nuplan. And we held out Carla as a test data set and ran reinforcement learning. We ran this self-play reinforcement learning that lets you train multiple agents jointly. I think the results are not super surprising, but like there's a success rate of RL agents in different environments when trained on different environments. You see that sort of the in-distribution performance is the strongest. So Nuplan training gives the best results on Nuplan, but also like all of them struggle a bit on held out data. And we kind of see that like even a simple strategy of mixing data from all the 3 training domains achieves like a superset, like a better result than any individual training data set. So I think we need more of this cross data set stuff. And lastly, like this was Buffer Drive was a simulator in the abstract bird's eye view space for traffic simulation. AlpaSim is another simulator. It's open source, but it also does photorealistic simulation. AlpaSim is going to have a challenge in 2026. This is like we're announcing this year, and this challenge is going to have very large scale held out evaluation environments, like beyond previous closed loop photorealistic simulations so far. So we're going to have two tracks for this challenge. There's going to be the physical AI AV, that's the very large data set I just showed you. In this track, we will have the data set with 25 countries that users can build with. And we will also leave this unconstrained in that you can submit here models that have been trained on private data or use closed source weights. This, like, we think will encourage some of the currently very closed companies that don't really want to use their policies towards like similar to how we see in LLMs. You kind of need to show your performance on benchmarks these days for LLMs to like be taken seriously. At the same time, we also support like the existing ecosystem. So I worked a lot on NavSim and a series of challenges in the last few years on that. We're going to kind of evolve that into a track in the AlpaSim challenge where you can use established, like there are hundreds of baselines already from the community, from people working on NavSim. You can just take these and deploy these models into this AlpaSim challenge. And maybe to quickly show you what the simulator looks like. So it's a photorealistic simulation based on 3D Gaussian splatting. Maybe I can zoom into one of these. I don't know how nice it looks on screen, but yeah, these are real recordings and you can re-simulate them. We have a policy driving in them. This is the AlpaMyo VLA policy I mentioned earlier, where it does this reasoning. Have a couple of other examples. But you can see that this is very different from sort of the Carla challenges and the previous challenges which we had in game-based simulators. You have like the ability to curate challenging scenarios, and we can put in scenarios in this private test set that are actually relevant or things where, for example, NVIDIA policies had a hard time, and those go into the test set, for example. So we're excited to see the community solutions on this AlpaSim challenge. And as I mentioned, the simulator is fully configurable. You can plug in other data sets, plug in other models. So the same AlpaSim simulator supports this new plan data set rendering. Yeah. All right, so this is it for my slides. Yeah, thanks to, this was a lot of open source work, and I couldn't mention everyone by name, but like the AlpaSim team, the Buffer Drive team, 123D, all of this work was done by huge teams of great people. So thanks to everyone, and like I hope this like really pushes the wheel forward. And yeah, if you're interested in this sort of like open source autonomous driving and building this open source autonomous driving community and stack, we are hiring at the new nonprofit. So you can find us at this link. Yeah, thank you.